Today's lesson is over polygons and quadrilaterals. So first thing, what is a polygon? So to be a polygon, it's got to fall under these criteria, or it has to have all of these criteria. So the first thing is it has to be a closed figure. Now, don't make this harder than it is. This is an open figure. And to make it a closed figure, that's a closed figure. So I've tried to describe this several times, and I think to describe it, it's really difficult. But anytime that it doesn't actually go back to the beginning, that's open. Anytime it is back to the beginning, that is closed. So it's got to be a closed figure to be a polygon. It has to be two-dimensional. Polygons are not three-dimensional figures. That is a whole nother can of worms that we're not going to get into this chapter. It cannot have any sides that are curved. So a circle doesn't work, or even if you do like a rectangle, doesn't make a curved area, that doesn't work. Any side that is not a straight line makes it not a polygon. Now this last one, the way it's written is a little bit confusing. It says it cannot have more than two sides intersect at one vertex. So what it means is this is a polygon. These two sides, this one and this one, intersect right here. So it says you cannot have more than two sides intersect at one vertex. So really what this is saying is you can't have something that looks like this. Because now, they're not just, these two sides aren't just intersecting at this vertex, we also have another intersection here in the middle. So I think this is written really confusing. Really all you have to make sure is that you have no sides that intersect each other. Now, that's what I say. I say you can't have any sides that intersect each other. Now, the reason they have to write it this specifically is because technically, two sides intersect here at this corner, two sides intersect here, two sides intersect here, two sides intersect here. But I guess for me, I would call those corners or vertices, whereas if they intersect this way, right here in the middle, that looks a lot more like they cross each other. So whichever way, again, maybe this is kind of like the closed figure where maybe just writing it up is easier to understand, or looking at the pictures are easier to understand than reading the words. That is a really good arrow. So circle all the polygons below. If it's not a polygon, explain why. So this first one, this first one is not a polygon, and it's because it's not closed. The second one is a polygon. It's closed. None of the sides intersect. It's not three-dimensional. What was the other one? I was going to forget. Oh, it has no sides that are curved. This next one is not a polygon because it's three-dimensional. So I guess I should cross these. So those are the ones that are not polygons. This one is. The next one's not a polygon. Now, again, I would say that the sides intersect. I guess if you want to, maybe a better way to say it is the sides intersect where it's not a vertex. Maybe is a good way to think about it. The next one's not, because it's curved sides. And the last one is because, again, it's closed, it has no curved sides, it's not three-dimensional, and none of the sides intersect unless it's at a vertex. So go ahead and pause this and do these on your own quick, then hit play to see your answers. This first one is a polygon. The next one's not a polygon because it's got curved sides. The next one's not a polygon. It can't have more than two sides that intersect at one vertex. And again, for me, the way I would describe that is I would say the sides can't intersect. Again, I know that's not the best of definitions, but that's the way I would still describe it. This next one is a polygon. Next one's not a polygon, it's not closed. And the last one's not a polygon because it is a three-dimensional figure. It has to be a two-dimensional figure to be a polygon. So the next one, we have a diagonal is a line segment that connects the non-consecutive vertices of a polygon. So first off, let's talk about non-consecutive. Non-consecutive, or I guess I should start with consecutive vertexes are the ones that are right next to each other. They're the ones that are connected by one of the sides. So those two vertexes are consecutive. They're connected by the sides. These two are connected by a side. So we're connecting the ones that are not consecutive to get a diagonal. So some of you guys probably wonder, why do we have to go over that? Because you guys already know what a diagonal is, and that's great. But it's pretty easy for the first one. We have two diagonals there, not a huge deal. But now it gets a little bit more confusing with this next one. So this next one, that line that just drew up there is a diagonal, because again, it connects two vertices that are not consecutive. They're not connected by one of the sides. So that would be another one that goes from the corner up to that first. The next one, I don't know if you can see it, but it went from here all the way over here. Now another one to that vertex, another one all the way to that one, and then another one again, it's hard to see, goes about here, and then one more. And so those are just the diagonals from this vertex over here. You could do the same diagonals from this one, from this one, from this one, and this one. It looks kind of like a mess, but those are all diagonals. And so that's why people say, why do we need to go over diagonals, the definition? Well, because it's actually a little bit more in-depth than you would think. So we'll talk about that a little bit later. So we have concave and convex polygons. So again, this is one of those other things that I think to talk about the definition, I think it's really hard, and I think it's hard to like describe and hard to hear someone talk about it or read words and understand it. But I think if you look at different examples and look at the pictures, I think it's going to be a lot easier. So convex polygons is a polygon where all the diagonals of the polygon are contained inside the figure. So if I connect every single one of these diagonals, notice how all of them are inside of your polygon. All of them are inside there. Concave is when the diagonals are outside, or if any of them are outside. So even if just one of them is outside, that's concave. So yes, I know that we have this diagonal, all those diagonals are all inside, but all it takes is one diagonal outside to say, nope, it's concave. Now again, for me, that's a great definition, and if you don't understand, you can try to look at those diagonals. That's a really good way to do it. But for me, it's also just pretty obvious if you look at the picture. If you look at the picture and it ever goes inward, that means it's concave. So these little parts go inward. One way I've described it is if you look at each vertex, it looks kind of like it's pointing outwards, pointing outwards, pointing outwards. If you ever have any that are pointing inwards, that means it's concave. Now again, there are several other ways to describe this, and so if you still don't understand after this, please talk to me or email me and I will give you some other descriptions, but I don't want to give you too much all at one time here. So are the following polygons concave or convex? This one is convex. And honestly, in my opinion, the hardest part about these isn't knowing what the definitions. It's not mixing those up, not saying, oh, it's convex when you actually meant concave. So one way to remember, obviously, is concave is where it's caved inward. So that one is concave. This one's convex, convex, concave, and convex. And again, if you want to look at drawing those diagonals on these concave ones, that's a diagonal that would be outside. This is a diagonal that would be outside. Any of the other diagonals on the convex ones will be all inside. So go ahead and do these on your own. Obviously, if you do these on your own, your answers are going to look different than mine. But to draw a concave polygon, literally just draw whatever polygon you want, and then make, and make sure it goes inward somewhere. Make sure there's a diagonal you can draw. That would be outside. Now that one's a lot more complicated. Most of you guys probably did one more like this. That's what I would have done. That's easier. A convex polygon is the exact opposite. So whatever you want to do, just make sure it is a shape that all the diagonals would be inside. Then draw a figure that's not a polygon. Now there's several different options for this. You can draw one with a curve. You can draw one that intersects itself. And you can draw one that's three-dimensional if you really want to something that looks a little different. I know that's sloppy, but I was going quickly. Or one that's not closed. Sorry, that was the fourth thing. Whoops. So the next thing we have is called a regular polygon. Now, we talked about these a little bit. We didn't use the word regular, but we've talked about equilateral and we've talked about equiangular when we talk about triangles. So equilateral, lateral is the sides. Equa obviously means they're equal. So all the sides are congruent to each other. That's equilateral. Equiangular, we talked about all these angles are congruent to each other. Again, we talked about that with triangles. So a regular polygon is both of those all in one. All the sides are congruent, and all these angles are congruent. Now, when you look back at triangles, some of you guys are maybe thinking, well, yeah, but when we talked about triangles, if it was equilateral, that made it equiangular. And if it was equiangular, that made it equilateral. So you can't have one without the other, so all of those would be regular. Now, with triangles, you're absolutely right. If you have a triangle that's equilateral, all the angles are also congruent, and vice versa. However, what about a rectangle? If you look at a rectangle, we all know a rectangle has these 90-degree angles. So aren't those angles all congruent to each other? Yeah, so it's equiangular. But are the sides congruent? No. If the sides were all congruent, it wouldn't be a rectangle, it would be a square. So that's one of the examples. That one is equiangular, but not equilateral. Now, last but not least, you have to know that they're congruent. You can't just assume. So for these, I marked those as we went through just to make sure you got that visual. But unless they put the little marks or unless they describe something or tell you something, you can't just assume that they're congruent. We'll talk about that here in a second with these. So label the following polygons as regular, equiangular, equilateral, or neither. Be most specific. Now, the reason it says that is because if you look at this first one, you could say all the angles are the same. So this is equiangular. Well, you're right, but it's also equilateral, which makes it regular. So when they say be most specific, I want the one that includes all of those. So this is actually a regular polygon. The next one's equiangular. The next one, it throws a lot of people off because they see the sides are congruent, so it is equilateral, but then they think the angles are all congruent because they're marked with these arcs. Well, they are, but they're actually, obviously, if you look, they're marked where they're not the same at all. So this is just equilateral. Now that brings us to this next pentagon here, this five-sided figure. This is what I was talking about earlier, where I said you can't just assume, I have to tell you. So this one, I don't put any marks there. I don't tell you that the sides are congruent. I don't say any of that. And so we can't just assume that. So this is neither. And there's some people that say, well, it obviously is, look at it. Well, if that's the case, then get out a ruler and measure this. How do I know that this one isn't 3 inches and this one's 2.9? Because technically, if they're different, that doesn't count. So that's why they've got to be marked. You have to make sure you're specific. And this last one is regular. The next one is naming the polygons by the number of sides they have. Obviously, triangle and quadrilateral, you should know. I'm hoping you also know pentagon and hexagon. Penta means 5. That's pentatonics. They have 5 members. Pentagram has 5. Anyways, penta means 5 and hexa is 6. So one of them you might not know is 7 is a heptagon or a septagon. 8 is an octagon, you guys should know that. 9 is a nonagon. 10 is a decagon. Now 11 is one of my favorites. 11 is just a 11gon. We'll talk about that in a second. 12 is literally my favorite. I think it's the coolest name. Dodecagon. 10 is a decagon. 12 is dodecagon. 13 is a 13gon. And then what's everything bigger than 13? Well, I just put an N, and so that N represents any number of sides you want. So anything that we haven't covered here, 14, 15, 16, 34, 94, 87, 1,756, all those are your N. Well, if it's an N number of sides, it's an N-gon. So if you have 45 sides, that's a 45-gon. If you have 1,000 sides, that's a 1,000-gon. Now, I don't know why they didn't just make it easier and say that a 12 is a 12-gon, an 8 is an 8-gon, a 9 is a 9-gon. I don't know. but this is just how we have to do it. That question always comes up where somebody asks, and I don't know why they made it hard for everybody. Now, naming polygons. Now, again, you should know this from when we did similarity statements, when we did some quadrilaterals, maybe some pentagons in there. To name a polygon, you have to start with any vertex. It doesn't matter which one. And then you list the vertices by either going clockwise or counterclockwise around the shape. So you could start with D right here, and you could call this D, E, A, B, C. Or you could start with D and go the other way around, D, C, B, A, E. That's totally fine. You could start at any other vertex and do the same thing. Start with B, C, D, E, A, or B, A, E, D, C. Any of those are fine. Just make sure you're not crossing over. Don't say B, A, C, E, D, or something like that. Make sure you're not crossing. So there is a ton of different ways you can label this, but what I always recommend is I always do it the same way. You don't have to by any means, but if you pick a way and you just do it the same way every time, it's going to make you miss less little tiny points because it's in your muscle memory. So I either start with the top one or the one that's kind of to the top right, depending on the shape. And then I always go clockwise. Now again, you don't have to do that by any means, but if you pick a way to do it and you always do it the same, it gets a little bit more developed in your muscle memory. And this last one, quadrilateral, a polygon with 4 sides is a quadrilateral. The sum of the angles in a quadrilateral is 360 degrees. Now, we're not going to get into it, but we also know that the sum of the angles in a pentagon is 540. The sum of the angles inside of a hexagon is 720, so on and so forth. So we learned earlier that triangles, the angles inside always added up to 180, but now we're learning that every shape has that. It's just a different amount. Now, for what it's worth, if you ever forget, the way they figured this out is if you make this into 2 triangles, that means this adds up to 180 and this adds up to 180, so the whole thing is 360. So solving for x. So the first way we're going to do this, we just know all of them add to 360. So x plus 113 plus 98 plus 42, 360. So that's the new step. Everything else is just algebra 1. So combine your like terms. 113 plus 98 plus 42 is 253. Subtract your 253 from both sides. You end up getting my x is 107. Now you can obviously check your work by plugging 107 in here, adding all those together to double check that you do get 360 degrees. So the next one gets a little bit more difficult. Instead of just having an x, we have these binomials, but that's okay. So we have 2x plus 25 plus 3x plus 5 plus the other two, it doesn't say what they are, but they're listed, or they have it marked as 90. So plus 90 plus 90 is equal to 360. And now we do the same thing we just did. So combine your x's. That's 5x. Combine your other ones. We have 25, 5, 90, and 90. Is 210. And subtract 210 from both sides. 5x is equal to 150. Divide that by 5. Your x is equal to 30. Now, if you want to check this one, you still can do that, but you have to plug it in. So plug 30 in for this x, plug 30 in for this x, and then add those all together. Now, to give myself a little extra room, I'm going to erase this little part right here. Same thing with this next one. We just have 4 binomials. But again, don't make it harder than it is. We have 5x plus 30 plus 10x minus 10 plus 6x minus 7 plus 8x minus 1 is equal to 360. So again, just like the last one, go through. We have 5 plus 10 plus 6 plus 8 is 29. We have 30 minus 10 minus 7 minus 1 is 12. And now we have a two-step equation. Subtract 12. 360 minus 12 is 348. Divide both of them by 29. You're getting x is equal to 12. So if you have any questions over that, let me know. But really, this last slide was the only slide that had algebra on it. Everything else has memorization stuff. So you're going to have to make sure you go over that, look over that, understand that, make sure you remember that.